Hello, Math 201. Today's lecture on section 5.4, working with integrals, will be a really quick lesson on just a couple little, first we're going to talk about kind of using symmetry to help evaluate integrals. And then the last thing we'll talk about is kind of the average value of a function, how the integral helps us calculate that. And then a little bit of kind of a montage, how would I say it? A throwback to the mean value theorem, but for integrals, but it's really just using the average value. All right, so let's remember what an even and odd function are. So I want to draw our attention over here. So an even function is a function where if you plug in negative x, it spits out the same thing as x. So that means that whatever I do on the right-hand side, it reflects over the y-axis and does it to the left-hand side. So if I plug any positive x value in, it does the same thing when I plug in a negative x value. So that's an even function. Classic examples of even functions are even polynomials and cosine of x. Those are the classic examples of an even function. And the really nice thing about an even function, when you integrate it over a symmetric bound, so if you have a symmetric bound, so it's the same thing, then really you're just doing this bound twice. And so you can just do 0 to a twice. And so, and a lot of times when you integrate with 0, it's way easier. And so that's nice with even functions. An odd function is a function that if you plug in negative x, it gives you the opposite value. And so an odd function is one that's symmetric about the origin. And so if you reflected along the origin and rotated it 180 degrees, it would do that. And so odd functions, if you plug in negative x, it gives you a negative function. And this has to be true for all x. And so odd functions are sine of x, x cubed, x to the fifth, x to the 2k plus 1. So odd polynomials and odd functions. The nice thing about integrating an odd function over a symmetric interval, so from negative a to a, is that this area is the same as that area, and one's positive, one's negative, so you get 0. And so that's really nice. And so using those kind of hacks allow us to integrate things relatively quickly. So for instance, this one, integrating this guy, this is an even function, this is an odd function, and so we can split it up into two integrals. So this becomes integral from -2 to 2, x to the fourth, and then minus, I'll do it like this, 3, and then -2 to 2, x to the third dx. There should be a dx here, sorry. This is an odd function, so this is equal to 0. So this equals 0 because x to the third is odd, right? So that's going to be 0. And then this is going to equal 2, and then I can integrate from 0 to 2, x to the fourth dx. And so what does that become? That becomes x to the fifth over 5. So 2 times x to the fifth over 5 integrated from 0 to 2. So you do that and you get 2 to the sixth over 5. And then minus when you plug in 0, but that's just 0. And that's it. And so using even and odd allow us to calculate that really fast. Whereas if I was to plug in these bounds into the antiderivative of that, it would actually be a lot of nastiness. And so using even and odd really helps quite a bit. How about this guy? So this one, we're going to break it up into two integrals, -pi over 2 to pi over 2, cosine x, and then minus dx. -4 integral from -pi over 2 to pi over 2, and then sine cubed x dx. And so this one, sine cubed x dx, why is this an odd function? So if you plug in, so this one's obviously even because it's just cosine of x, but the sine cubed of x. So f of x equals sine cubed of x. How do we check it's odd? Well, what is f of negative x? That's sine of negative x, and then sine cubed of x, remember, is you cube the whole thing. But what is sine of negative x? Sine of negative x is negative sine of x, and then that whole thing cubed. But if you cube a negative, that just becomes negative on the outside, and that becomes negative sine cubed of x. But that really is just negative f of x. So it is odd. So sine cubed of x is odd. So therefore, going back to this integral. So plugging this, oops, not image. Whoops, that's not what I want to do. Whatever. It looks kind of funny, but that's fine. So what's this going to equal? It's just going to equal the integral from 0 to pi over 2 cosine of x, and then minus 0. There's a dx here. I always forget the dx, and students do all the time. So just be careful with that. Whenever you're integrating something, there needs to be a dx there. And so then that integral is going to be sine of x evaluated from 0 to pi over 2. And then plug in pi over 2, you get 1. Plug in 0, you get 0. This is 1. And so that whole integral is just 1. So it looks super disgusting and it looks like it was going to be gross, but because of this using the odd function, even function, it's really easy. All right, now let's talk about average value function. So here's the kind of way to think, kind of motivation. If you have 5 people, 1, 2, 3, 4, 5, their average mean weight is you add up all their weights and then divide by the number of people and you get their average weight, right? You can actually naturalize this to a function or generalize this to a function. And the idea is that if you picked a bunch of points on the partition and then you take the function value at all those points and add them all together and divide by n, what happens is that if you just take the limit as n goes to infinity, which we can do by realizing that n is b minus a over delta x, and then it actually becomes the Riemann sum, or this is the Riemann sum part, and then 1 over b minus a, then the average value really just becomes 1 over b minus a, and then times the definite integral. And so the average value of a function is 1 over the length of the interval, and then times the area under that function. And so where does this kind of come from? The idea is that if you took the area from a to b under a function, this is that green area, there is some rectangle height such that this rectangle has the same area as this green, where this little red makes up for that little green that's right there. And so this height right here, that is the average height. And so the area of the rectangle is the average value times b minus a, and that's equal to the area under the function. And so let's use this in an example. So let's say that a hiking trail has an elevation given by this, where f is measured in feet above sea level and x represents horizontal distance along the trail between 0 and 5. What is the average elevation of the trail? Well, f bar, remember by definition, is 1 over the length of the trail, which is 5 minus 0, and then times the integral from 0 to 5 of this function, 60 x cubed minus 650 x squared plus 1200x plus 4,500 dx. And so we can integrate that. That's not hard. It's 1/5 integral, or sorry, we're going to do the integral. Becomes 60 over 4 x to the 4th minus 650 over 3 x to the 3rd plus 600 x squared plus 4,500 x evaluated from 0 to 5. And so our final answer is just plug in 5. So it's 1/5, 60 over 4, 5 to the 4th minus 650 over 3, 5 to the 3rd plus 605 squared plus 4,500 times 5. And that's our final answer. I could look up real quick what that actually is. So I think that that is what is that actual value? It's roughly, so copy. So in case you're curious, that's what it roughly is equal to. It's roughly 3,958 feet. And so that's what the average elevation is. And so all we do is we just integrate the elevation and then divide by the length of the interval. And then the last thing I want to talk about is the mean value theorem. So we said that there exists this average height. And so it turns out that there's always going to be some x value, or we call it c, some c, which is an x value, where the average height is attained. And so if you have a continuous function on an interval, there is some c value that's going to attain the average value. And so this is called the mean value theorem for integrals. And so let's do a real quick example of it. So find the points on the interval 0, 1 for which equals its average value. So let's find the average value. So f bar is equal to 1 over 1 minus 0, the integral from 0 to 1 of this function, which is 2x minus 2x squared dx, which is, that's just 1 on the outside. And so it's the integral of 0 to 1. For that one, we can just do. So it's just x squared minus 2/3 x cubed evaluated from 0 to 1, which equals 1 minus 2/3, which equals 1/3. So the average value of this function is 1/3. And so we want to find x in the interval 0, 1 when 2x times 1 minus x equals 1/3. And so how do we do that? Well, our favorite thing, we set them equal and solve for x. So you get 2x minus 2x squared equals 1/3. Bring everything over to one side. And so you get 2x squared minus 2x plus 1/3 equals 0. So everyone's favorite, the handy dandy quadratic formula. So x equals negative b, so 2 plus or minus square root of b squared, 4 minus 4ac. So that will be 4 times 2 times 1/3, so 8 over 3. And then all over 2a, which is 4. And so that is, we'll just leave the answer at that. And then I'll show you this picture. So what those values are roughly equal to, it's like roughly 0.2 something and 0.7 something. So actually I have the answer. So let me just do it real quick. Oh, wrong one. So what those two values are roughly. Oh, did I not do the exact values? No. Okay. So we just leave them exact. And so that's what those two values are. And so the two values are x equals 2 plus the square root, and then so that's 4/3 over 4, and then x equals 2 minus the square root of 4/3 over 4. And so those are what those two values are right there. And so those are the two values guaranteed by the mean value theorem. And that's all you need for the homework for this week. All right, take care.